Alrighty, so we're going to continue with the lesson on derivatives of inverse trig functions, and in this video I am going to show and prove the derivative of the tangent inverse function. Okay, and we're going to do this a little bit differently in the other video. That was a little bit longer because I wanted to show you some of the underlying concepts, and here we're going to be able to just kind of speed up the process just a little bit more. Okay. So for the derivative of the tangent inverse function, we're going to start out by making an equation. Theta is equal to tan inverse. Okay? And remember, we are inputting a ratio and we're getting out an angle. So I've chosen theta here. So what that means then is the tangent of theta is equal to x. Okay? In other words, if you use x as the input into the inverse, then x must be the output of the tangent function. If theta is the output of the inverse, then theta must have been the input of the original function. And again, what that means then is that we have a right triangle. It doesn't matter what angle you pick as the reference, just pick something. So let's say that's the reference angle. Then what this means is that the ratio opposite over adjacent must result in x. So one of the opposite length is x, the adjacent length is 1. And just for us to complete this, that means the hypotenuse is 1 plus x squared square root. Okay. Now, again, we want to use implicit differentiation to find the derivative of tan inverse. In other words, d theta over dx. Okay. Since theta is written in terms of x, we want to take the derivative of this function in terms of x. And rather than using it here, using it up here, we're going to take the derivative using this result right here. And I'll show you why that works, and it actually is quite simple. So the derivative of the right-hand side is just 1. The derivative of tangent, hopefully you were able to jump in and get that answer right away. If not, you should study these derivatives. But it is the secant squared of theta. And then remember that theta is a function of x, so we still have to multiply this by d theta dx. Okay? And this quantity, d theta dx, is what we're going to solve for. Well, this works out, and then now we're going to convert everything back into x. Okay, so convert variables to x. Okay, so this theta here, secant squared of theta, well, the secant is the hypotenuse divided by the adjacent side, and that's squared. So this is just 1 plus x squared d theta dx equals 1. One more step, doing some basic algebra, d theta dx is then equal to 1 over 1 plus x squared. And there you have it. The derivative of the tangent inverse is actually this expression right there. So let us do a relatively quick example here, and we're going to find the derivative of this expression. So we're going to use the rule that we just proved. So this is f prime of x is equal to 1 over 1 plus, okay, and it's this entire expression squared, 3x squared plus 2x quantity squared. But then we still have to take the derivative of the inside function and multiply by that. So that is 6x. So you still have to use the chain rule, product rule, quotient rule. All of that still applies. Okay. And then now I'm going to do a little bit of simplification. I suggest you hit pause and simplify it yourself, and then hit play again to see if you got the same thing I did. Okay, so there you have it. That's the derivative of the tan inverse of 3x squared plus 2. This step here comes from applying the rule that we just proved. This is multiplying by the derivative of the inside function, so the chain rule and all that good stuff still apply. And then I did some simplification. Your homework for tonight is going to be to find the derivative of the following functions with proof. I know you could probably look these up somewhere and eventually you're going to have to memorize them, but it's a good exercise for you to convince yourself why the result is true. Okay. Thank you for watching and have a wonderful day.